So like I said, this involves a little bit more expensive, hardcore hardware, specifically, high voltage transmitters that sort of mimic the exact same frequency patterns that we see on certain access points, and will just completely bombard their surrounding area with just white noise, with static that inherently causes packet collision, packets to drop, they can't retransmit, and the whole network is kind of flooded with noise. And it's not like data noise, it's just sort of radio frequency noise. And why would someone do this? They would either do it for fun, for hacktivist reasons. You can also use it for spying in order to collect a packet, sort of analyze it, put your jammers on to sort of stop the packets from retransmitting, check the packet, inspect it, decrypt if you have the capabilities of decrypting it. And that would be sort of some of the reasons why you would use a wireless jammer. And in these pictures here, you can see that they come in all different sizes. You can have some portable ones that have a battery supply attached to them. And this one here, these ones are actually really fun because they actually jam not just Wi-Fi, but they'll also jam 3G, 4G, LTE, Wi-Fi, Bluetooth, you name it. And obviously, you know that the military and the police use them for a lot of different scenarios as well. These are highly illegal, and you cannot have them or use them or turn them on in any sort of public area because it's extremely dangerous. I'm pretty sure it's not really good for your health either. The next type of attack is obviously an active attack. It's a frame injection attack. This is just a picture of Wireshark, a packet sniffing software. And right now it's configured to listen on one of its wireless networks. And the way that this attack kind of works is an individual will sort of bypass the standard way of interacting with the base station. There are these really strict modes, SIM, station infrastructure mode, which doesn't even allow you to directly talk to other clients. It has strict rules that govern how you can actually conduct all of your packet transmission, and it's usually between just you and the client, or you and the access point. What a lot of attackers will do is they'll escalate their wireless privileges into something known as monitor mode, which allows them to listen to not just traffic between me and the access point, but everyone else that's connected to the access point. I'll be able to look at those packets. Obviously some of them are going to be encrypted. I won't be able to see what's in them, but there is sensitive information in these packets. There's MAC addresses, URLs that people are trying to hit, passwords are being sent back and forth. The next type of attack, so we've all heard of denial of service. This one, it's not as well known because it's targeting a specific type of network. And this attack is called denial of sleep. Wireless networks are great because they kind of cut us off from that cable. And, whether it's to, make our offices look aesthetically more pleasing or just make it a little more convenient, it's a great tool. So obviously it's used in a lot of sensor networks where many sensors are deployed within a massive area, whether it's a field or a battleground. And these wireless sensors aren't hooked up to your typical power outlet. They'll have an independent or an isolated power system, kind of like a battery attached to them. And these sensors will grab information and relay them via Wi-Fi to their central node, which is connected to the wired connection of whatever centralized network or server is managing them. So a denial of sleep attack is a type of attack where if I were to perform it, I would be driving around this field or using a drone, and I would be targeting these sensors with these Wi-Fi cards, and I would be actively playing with them and telling them to work a little extra harder. So their transmitters are utilizing more power. I'd be telling their MAC addresses to change your sleep time, because if you're not being used, the wireless card's actually kind of throttled down. They're not utilizing any power, so I'm kind of running them dead. I'm taking their lifetime and I'm running it short. So that's the type of denial of sleep attack. And what you're doing is you're essentially just destroying the performance of this entire network. So you can see here wireless cameras, infrared cameras, microphones, all these things kind of utilize this wireless network that's based off of a battery. Next type of attack is a collision attack. A lot of routers, a lot of Cisco routers, Linksys routers have a collision avoidance system where when they're being spun up, they'll look around them and they'll say, okay, I've got a couple of routers that are on channel 1, channel 5, channel 11. I'm going to sit right here at 4 because there's no one really here. And this avoids collision packets, allowing the router to sort of speak freely with all of its clients. But what an attacker will do is they'll post up really close to this access point, and they'll have a rogue access point that will detect the channel in which this access point is, the targeted access point is operating on, and it'll try its best to replicate the exact pattern of its radio frequency, and it will just boost out a whole bunch of noise. And not like a radio frequency jammer type of noise, actual data packets that it'll hopefully collide with the network and cause them to retransmit, resend. And I'm sure that a lot of people who either live in an apartment or a condo who have a lot of routers that are all pretty much really stacked really close to each other will know that your wireless network will kind of be hindered. Its performance will be a little bit slower just based off of how many wireless networks are around you. A lot of false positives will come up with this type of test or this type of attack because something as simple as any cordless device that's really near an access point or a client can cause this type of collision attack. But there are some actual attackers who will use this technique to hinder the performance of a network. It's a desynchronization attack where this is a type of packet injection attack, but we're specifically looking at changing control flags and sequence numbers in order to forge messages between the access point and the client. What this kind of does is, if you're changing sequence numbers, you're interrupting the natural flow of the network and how it inherently operates, causing these packets to not be accepted by the access point or the client. The checksums don't match, and they'll have to retransmit it again. So by doing this sort of desynchronization attack, it is highly technical, and it does take a lot of time. You're probably not going to get a good return on investment in terms of an attack perspective, but it's good to understand that you are able to change these, really low-level OSI sort of parameters like a control flag, like TCP streams, UDP streams, in order to perform later, more advanced attacks, a flooding attack. And the way that a flooding attack works is a malicious node will try to send out as many packets down the network as it can, targeting as many nodes to do the exact same thing. Let me just close this here. And it's kind of like an internal DOS attack. It can send out these packets and try their best to route and attack a certain target within that network. And the way that these flooding attacks will work is I could go ahead and spoof any one of the client's MAC addresses and say, I want to send a deauthentication packet. And the router will just accept it, send it back down saying, okay, there you go, you're deauthenticated. Now, it'll look like as if the clients themselves are trying to commit suicide on the network. But what's really happening is there's just one person out there who's just looking at everyone on the network, wrote a quick little script, or an exploit's out there already, and they're just sequentially, spoofing these different MAC addresses, and they're sending these deauth packets, and it's inherently flooding the access point, causing the access point to fail. The replay attack, this is the type of attack where it's mostly vulnerable, or it's mostly susceptible to networks that are not of modern standard. So the way that it works is I'll be listening in on a network. I'll grab some sort of encrypted packet that looks like, okay, this is obviously a packet that was used for some sort of authentication process, and if I use it again, I'll be able to authenticate myself. So if Alice tries to send Bob an authentication packet that Bob sort of requested before logging Alice in, she sends out this sort of encrypted packet. If I go ahead and I copy this packet, because I'm listening to the network, I can store that, and I can wait for maybe a day or two, and wait for Alice to sort of, fall offline or just not be online at the time, and I can send that packet to Bob, and hopefully Bob will authenticate me, thinking that I'm Alice. Sort of the ways that we've kind of prevented this type of replay attack is through session tokens, time stamping, and one-time passwords that aren't used, over and over again. This is another type of attack where a node has become compromised, and that node is a central part to the routing of how the entire network flows. So you can see here in this diagram the red node, it acts as the malicious node, which will selectively drop or reroute packets that it's given. This type of attack, it's really hard to detect because it could be randomly, doing its job, or it could then decide, no, I'm just going to go ahead and not do my job. So it's hard for network administrators to really boil down where this selective packet dropping is happening, and this can be easily used for information gathering. If client A wants to talk to client B and they have to get through me, I can say, half the time I'm going to grab these packets, I'm going to store them, and I'm going to create a huge database of all these packets and do a history check once I can decrypt them and see what's going on. So that's a selective forwarding attack. Next one here is a wormhole attack. And the way that this attack happens is an attacker will sort of look at what's happening on C9 and copy that exact packet and find out that its destination is actually going to S2. Now, if it had a tunnel or some sort of direct line or a faster connection to S2, then it could then alter S2's routing tables, and not just S2's, but all of S2's neighbors will then say, I'm gonna totally bypass all these other nodes in here, and I'm going to send all my packets through this wormhole tunnel to all these other nodes instead of taking the route that was originally orchestrated in the architecture of the network. The next attack is a sinkhole attack, and the way that this works is one compromised node goes onto the network and it tries its best to grab all the packets and have them directed towards me, towards the sinkhole. And what it does is it's effectively grabbing all these packets and rerouting traffic to itself. This type of attack can be combined with a selective forwarding attack, where these packets that are being collected by this sinkhole could then be forwarded and routed off to a different remote location through a wormhole into a completely different network. So you can effectively be sitting with an iPhone or a laptop somewhere in a network and just leave this sinkhole just sitting there, stealing all these packets that are going through the air, and effectively copying them and rerouting them into your own private network somewhere else. So maybe it's not such a bad idea right now, but if something like that WEP encryption standard, like RC4, gets broken, if we see like AES with like our higher computing power start to break down some of these modern standards of algorithms that we're using, we could effectively be hacking what the past was. If I logged into my Facebook today, could I hack into that, a month from now, if I was inherently stealing all these packets now and just storing them off in some remote location? Sounds like some NSA stuff, right?